Imagine lying inside a massive, a thrumming fMRI tube.
Oh yeah, totally still.
Right, exactly. You are completely still. Your eyes are closed. You aren't solving math problems or, I don't know, reading a book.
You're definitely not listening to music in one of those things.
No, not at all. You are doing absolutely nothing. Yet, if we look at the computer screen in the next room, we don't see a quiet, resting organ.
Far from it.
Yeah, we see a system that's it's boiling with these chaotic, unpredictable electrical and chemical storms.
It looks like pure static to the naked eye.
Literally just static. And for decades, if you wanted to look at that static and find the exact biological signature of, say, a psychiatric condition, you were largely out of luck.
Which is, it's incredibly frustrating for everyone involved.
Because there's no jagged white line like you get with a broken bone on an x-ray, right?
Exactly. We crave that visual proof. Doctors and patients alike, we want to point to a scan and say, right there is the source of the problem.
But when you step into the world of complex neurodevelopmental or psychiatric conditions, the diagnostic landscape just becomes, incredibly murky.
Because the markers of dysfunction are buried deep within that constantly shifting sea of activity you just described.
And that brings us to the massive, incredibly diverse stack of sources you've handed over to us for this deep dive.
It's quite a stack.
It is wild, because what you've given us is essentially a treasure map for navigating those muddy waters.
I like to think of it that way, yeah.
Looking at this reading list, on one hand, we have this highly technical research on deep learning architectures trying to interpret that fMRI static.
And on the other hand,
we have papers detailing the underlying neurochemistry of how the human brain actually pays attention. We're looking at the psychology of deep work and then tying it all together with the biological necessity of sleep.
I know. It looks totally disparate at first glance.
A computer science paper next to a psychology book next to a neurobiology study.
Right. But the underlying thread connecting them all is profound. The mission of this deep dive is to map the hidden dynamics of the human brain.
And we're doing that by looking at how a cutting-edge artificial intelligence framework is currently attempting to do the exact same thing.
We're looking at a deep learning model that has finally learned to read the storms.
I really want to break down how this AI actually pulls this off, because it's not just a matter of, feeding a computer a bunch of brain scans and asking for an answer.
No, not at all. It's a very specific sequence.
Right. So we're going to trace the AI's journey. We'll start with how the AI learns to define a normal baseline brain out of all that mathematical noise.
Which is a huge hurdle in itself.
Yeah. Then we'll see how it identifies specific dysfunctions, and crucially, how it explains its own math.
The introspection part.
Exactly. From there, we'll unpack how this system solves a massive engineering problem called vanishing saliency, which threatens to ruin its memory.
And finally, we'll contrast what this model discovered when it looked at Alzheimer's, schizophrenia, and autism.
And the most compelling part of this framework is that we aren't just talking about code, are we?
No, we really aren't. At every single turn, the problems this AI faces and the solutions the engineers built, they perfectly mirror our own biological reality.
Right. So we are going to hold up a mirror to you, the listener. We're exploring what it actually means for you, biologically and chemically, to focus your attention.
To succumb to mental fatigue, to consolidate a memory while you sleep.
And ultimately, what it means to be conscious. It's a journey from the raw, chaotic data of an fMRI scanner all the way to the lived human experience.
Let's just start with that raw data, because I think people really underestimate just how messy a brain scan is.
Totally. When the AI boots up and looks at a resting state fMRI, what does that actually look like mathematically?
Well, the researchers in our sources refer to it as the curse of dimensionality.
The curse of dimensionality. Sounds ominous.
It kind of is for data scientists. When you take an fMRI, you're capturing the brain's activity in three-dimensional space over time. You're tracking blood oxygen levels.
Okay, so a 3D movie of blood flow.
Basically. The scanner divides the brain into hundreds of thousands of tiny 3D pixels. We call them voxels.
Voxels, got it.
And you are recording the fluctuations in every single one of those hundreds of thousands of voxels, second by second, for minutes on end.
So the sheer volume of numbers is just staggering.
It's an absolute ocean of data points.
But wait, why is that a curse? I thought deep learning models love massive amounts of data. ChatGPT trained on half the internet, right?
Right, but the curse comes from the ratio of features to subjects.
Yeah.
In language models, sure, you have billions of words and millions of documents.
Right.
But in medical neuroimaging, getting people into an fMRI machine is incredibly expensive
Yeah.
and logistically difficult.
So you don't have millions of brains to look at.
Exactly. You might have millions of high-dimensional data points per subject, but your dataset only contains like a few hundred actual people.
Ah, so if you feed that into a standard machine learning model,
It crashes into a wall of overfitting. It doesn't learn the underlying patterns of a disease at all.
it just memorizes the specific noise and quirks of those, 200 specific brains.
Exactly. It memorizes instead of learning.
Okay, so you can't just dump the raw video feed of a brain into the AI. You have to clean up the ocean first.
You really do.
The sources talk about a pre-processing technique called Spatial Group Independent Component Analysis, ICA.
Yes, ICA.
Help me visualize what ICA is actually doing to those hundreds of thousands of voxels.
Okay, think of a crowded cocktail party.
Love a cocktail party.
Right. So you're standing in the middle of a room, 50 people are talking at once, glasses are clinking, music is playing in the background.
Sounds loud.
Very. Now, if you record that room with a single microphone, the audio file is just one incredibly complex, messy waveform. It's essentially noise.
Okay, so how does ICA help?
ICA is a mathematical operation that takes that single tangled waveform and separates it back out into 50 individual distinct voices.
That's a great analogy, but how does the math actually know what a voice is compared to, say, a clinking glass?
It looks for statistical independence. It analyzes all the fluctuations and finds signals that behave independently of one another but still have their own internal consistency.
So when applied to fMRI data, it's looking at the chaotic flashing of all those voxels.
And it groups together the areas that consistently fire in synchrony. It separates them from background physiological noise, like a heartbeat or head movement.
So instead of 100,000 random pixels, the researchers use ICA to isolate specific networks that are speaking together.
Exactly. They isolate exactly 53 intrinsic functional networks. These are distinct channels of communication across the brain.
Wow. So the AI is no longer looking at a sea of pixels.
Right, it's looking at 53 clear, continuous time series signals. It's like having 53 individual heart monitors, but for brain networks.
Okay, that makes sense. The data is clean. But we still have that dataset size problem, right?
Unfortunately, yes.
If you take those 53 clean signals from a dataset of just, say, 150 patients with schizophrenia, the deep learning model is still going to overfit.
Oh, absolutely. It's way too small a sample to learn a complex disease from scratch.
So how do they get around that?
This is where the researchers introduced a brilliant pre-training framework. They use a model they call the whole MILCL model.
MILCS.
Like thedring, spelled MILC. It stands for Maximizing Mutual Information Local to Context.
Okay, that is a mouthful.
It is. But the concept is simple. Because the disease datasets are so small, the AI needs to understand what a normal brain looks like first.
Oh, before it can possibly find the anomaly, it has to deeply mathematically understand the baseline.
Precisely.
So where do they get this baseline? Do they just find a bunch of healthy volunteers?
They take this whole MILC model and pre-train it on a massive, completely separate dataset called the Human Connectome Project.
Human Connectome Project, that sounds huge.
It contains functional MRI data from over 800 healthy adults.
I see. I think of this like trying to find a wrong note in a jazz improvisation.
Oh, that's a good way to put it.
Yeah, if you've never heard music before and someone plays a dissonant jazz chord, you have no idea if it's a mistake or part of the song.
You'd just be confused.
Right. You have to learn the underlying rules of rhythm, harmony, and scale first. The Human Connectome Project is basically the AI's classical music training.
It really is.
But how does it learn without a human teacher? The paper says this whole process is self-supervised.
The self-supervised objective is what makes MIL so powerful. The AI is tasked with maximizing the mutual information between a tiny local window of time, say 3 seconds of brain activity, and the entire global sequence of that person's scan.
Wait, let me stop you there, because maximizing mutual information sounds like a textbook.
Fair enough.
Translated to human terms, is the AI basically trying to guess the overarching vibe of a whole song just by listening to a 3-second audio clip?
That is a very accurate way to frame it. The AI takes a short snippet of those 53 networks firing, and it analyzes it against the global fingerprint of that entire scanning session.
So it's looking for the connection between the micro and the macro.
Yes. It tries to find the underlying patterns that connect the local moment to the global state.
And it does this over and over.
Millions of times across 800 healthy brains. Through this, the AI learns the fundamental rhythm, flow, and architecture of a functioning human mind.
Which brings us to our first biological mirror. I love this part.
Me too.
When this AI is analyzing the baseline dynamics of a healthy brain, what invisible forces is it actually seeing? Because a resting brain isn't turned off.
Not at all. A resting baseline brain is a massive engine of consciousness and arousal.
Even staring at a ceiling in a scanner.
Even then, your brain is actively maintaining a state of readiness, processing internal thoughts, monitoring the periphery. To understand what the AI is mapping, we have to look at the psychological and chemical realities of that baseline.
Our sources bring up a fascinating framework for this. The global workspace theory, proposed by Bernard Bars. I love this theory because it gives a shape to consciousness.
The global workspace theory asks us to imagine the mind as a theater.
Okay, a theater.
Consciousness itself is the stage, but the entire stage is pitch black except for one bright spotlight.
And that spotlight is?
That spotlight is your attention.
And everything outside the spotlight is just, what, sitting in the dark?
Exactly.
Yeah.
All your unconscious processing is in the dark theater seats.
Yeah.
Your memories, your sensory inputs, your automated motor routines, they're all active, but they are competing with each other to get onto the stage.
Like actors waiting in the wings.
Yes. And when a piece of information successfully steps into that spotlight of attention, it gets broadcast to the entire theater.
That moment of broadcast is when you become consciously aware of a thought or a feeling, right?
Exactly. The baseline brain the AI studies is essentially the hum of this theater operating normally. The spotlight smoothly gliding around, bringing different thoughts into awareness.
If the AI is tracking the dynamics of this theater, what is the electricity powering that spotlight? What are the neurochemicals actually pulling the levers to move it?
The primary fuel for that spotlight is acetylcholine, often abbreviated as ACO.
Got it.
It's fascinating because the brain actually has very few A-chip producing cells. They're mostly clustered deep down in the older primitive brainstem areas.
But they have long cables reaching everywhere else, don't they?
Huge reach. Their axons project outward to almost every single region of the cortex. When they release acetylcholine, they fundamentally alter the signal-to-noise ratio in the brain.
Okay, explain signal to noise in a real-world scenario. Let's say I'm sitting in a noisy coffee shop trying to read a dense research paper.
Perfect example. Your visual cortex is receiving a flood of data. The words on the page, the people walking past your table, the barista wiping the counter.
That's a lot of input.
Right. Acetylcholine acts specifically in those sensory regions to boost the strength of the neural signal representing your target, the text on the page.
It turns up the volume on the signal.
Yes, but turning up the volume doesn't help much if the background noise is also loud.
Very true.
Which is why acetylcholine's second function is so critical. It actively inhibits the nearby neurons that are processing the distractions.
Oh, it suppresses the noise of the coffee shop.
It sharpens the edges of the spotlight, so the text is brilliant and the periphery fades away into the dark.
Okay, so acetylcholine locks the beam in place, but the sources also heavily feature dopamine.
Dopamine, so misunderstood.
Right. In pop culture, dopamine is just the reward chemical. You check your phone, you get a hit of dopamine. How does that relate to a theater spotlight?
Yeah, the pop culture definition of dopamine is severely limited. In the context of attention, dopamine is what makes the spotlight flexible.
Flexible how?
Acetylcholine gives you the lock-on, but dopamine primes the brain for vigilance. It gives you the ability to shift that focus intelligently.
Oh, so it moves the beam.
The research indicates that dopamine helps you utilize prior knowledge to dictate where the spotlight should go next. Without dopamine, your spotlight would get stuck on a single thought and never move.
Okay, so dopamine moves the beam, acetylcholine sharpens it. But this entire system operates under the influence of a much broader state, doesn't it? Our level of arousal.
Arousal is the foundational baseline. To understand it, we look at the Yerkes-Dodson law. It's a classic psychological principle.
The bell curve one, right?
Exactly. It dictates that there is an optimal level of arousal for performance, shaped like a bell curve.
So if you're completely unaroused, say you just woke up and you're super groggy, your performance is terrible, the spotlight is too dim.
And if you're over-aroused, like in a state of sheer panic, your performance also plummets.
So the peak of the bell curve, the optimal spotlight, is right in the middle.
Right in the middle.
The sources bring in something called the Easterbrook cue utilization hypothesis to explain what happens on the far side of that bell curve when stress takes over.
Easterbrook's hypothesis perfectly describes the collapse of the spotlight under high stress. As arousal levels climb too high, our attention mechanically narrows.
The brain begins dropping peripheral details.
It focuses exclusively on the most central, highly arousing cues of the situation.
So if I'm hiking and a bear steps onto the trail, I immediately stop noticing the sound of the birds or the color of the trees.
You definitely shouldn't be looking at the trees,
Right. The spotlight shrinks to a laser point directly on the bear's teeth.
which is great for immediate survival. But it's terrible for complex decision-making because you are now completely blind to relevant peripheral information.
Like the alternative escape route to my left.
Exactly. Your cognitive flexibility disappears. And what is truly wild is how this baseline level of arousal varies from person to person.
Oh, this was my favorite detail in the sources, the Ivan Pavlov studies.
Most people just know the dogs and the bells.
Yeah. I grew up thinking Pavlov just rang bells to make dogs drool. I had no idea he was doing deep physiological research on temperament.
He conducted extensive studies on the nervous systems of different dogs. He categorized them into temperaments that align with historical human labels like melancholic or choleric.
And he found something deeply counterintuitive, didn't he?
He did. He observed that melancholic types individuals who might appear outwardly withdrawn, quiet, or unresponsive to their environment were actually experiencing intense, overwhelming internal arousal.
Their internal theater is already blaring at maximum volume.
Yes. So the nervous system produces an inhibitory response to the outside world. They essentially board up the doors to the theater to protect themselves from sensory overload.
They aren't under-aroused at all, they are maxed out.
Whereas the choleric types, the people who are constantly seeking thrills, getting aggressive, or reacting loudly to everything,
What's their baseline like?
their internal baseline is actually much lower. They require massive amounts of external stimulation to push them up the bell curve to their peak arousal state.
That is fascinating. So let's bring this all back to the computer.
Right, the AI.
When our deep learning AI is pre-training on those 800 healthy brains in the Human Connectome project, it isn't just crunching abstract math.
No, it's mathematically capturing the intricate, invisible dance of all these biological systems.
It's learning the rhythms of acetylcholine sharpening the signal, dopamine shifting the beam.
And the fluctuating levels of arousal dictating the width of the spotlight. It has mapped the baseline engine of human consciousness.
Which means the AI is finally fully prepared. It knows what the normal hum of the theater sounds like.
It is ready to be unleashed on the disease data sets. It's ready to find the dysfunction.
So the researchers transition the model. They use a concept called transfer learning.
Yes. They take this whole MILC model, which is now an expert in healthy brains, and they expose it to much smaller data sets.
Like, they have one data set for schizophrenia, one for Alzheimer's, and one for autism.
Because the model already speaks the complex language of the brain's baseline, it doesn't need 10,000 patients to figure out what Alzheimer's looks like.
It leverages its vast prior knowledge.
Exactly. The researchers found that the model achieved incredibly high accuracy in separating the healthy control patients from the patients with the disorders.
But this is where the medical community usually throws up a massive roadblock, right?
Oh, absolutely.
If a doctor looks at a patient and says, "You have schizophrenia because this black box algorithm spat out a red light," the patient is going to say, "Show me the proof."
And they should. Just being accurate isn't enough in medicine. We need to know why the AI made the decision.
We need the math to explain itself.
This challenge gave rise to the field of AI introspection, or explainable AI. The engineers needed to force this deep learning model, which consists of millions of invisible weights and biases, to hand over its notes.
How do they do that?
To achieve this, they utilized a post hoc explanation method known as integrated gradients, or IG.
Okay, let's translate integrated gradients. Let's say the AI has just stamped a big schizophrenia label on a brain scan. How does IG extract the Y from the machine?
Imagine the AI's decision-making process as a physical landscape, a complex terrain of hills and valleys.
Okay, I'm picturing it.
The AI is currently standing at the very top of a specific hill. That peak represents its final decision that the patient has schizophrenia.
Right.
Integrated gradients essentially forces the AI to walk backward down the hill step by step, all the way down to a flat, neutral valley floor.
What represents the valley floor in an fMRI? Like a dead brain.
Usually, the neutral baseline is a completely blank mathematical state, like an array of zeros.
Ah, okay, you're right.
As the AI traces its path from the zero state back up to the schizophrenia decision, it calculates the steepness, the gradient at every single step along the path,
So it looks at every voxel, every network at every second in time.
and measures how strongly that specific piece of data pushed it upward toward the final diagnosis.
So it's assigning an importance score. It says, network 12 barely pushed me up the hill, but network 47 at minute 2 shoved me directly toward the diagnosis.
And by aggregating all those gradients, it generates a saliency map.
A heat map.
Exactly. It provides a heat map that points to the exact moments and spatial interactions in the fMRI data and says, this right here, this specific dynamic is the core reason I made my choice.
I have to play devil's advocate here, though, because this sounds like we're just trusting the AI's self-reporting.
Does sound like that, doesn't it?
How do we know the AI isn't just, hallucinating? How do we mathematically validate that the parts of the brain it claims are salient are actually the biological markers of the disease and not just random noise it fixated on?
That skepticism is exactly what drives rigorous AI research. The team knew they needed irrefutable proof, so they developed a validation framework called RAR-R.
RAR, retain, and retrain. Walk us through RR, because the methodology here is aggressive.
It is ruthless. They took the saliency maps generated by the AI for a specific data set. They ranked all the data points based on how important the AI claimed they were.
Okay.
Then they retained only the absolute top 5% most salient data points.
Just the 5% most important moments. What did they do with the other 95% of the brain scan?
They literally replaced it with zeros. They blanked it out entirely.
Wait, hold on. If you replace 95% of a continuous brain scan with zeros, aren't you essentially handing the computer a dead brain?
Pretty much.
How does the secondary model look at 95% flat line and 5% isolated flashes and make any sense of it?
That was the ultimate test. They took this stripped down, 95% dead data, and they fed it into a completely independent traditional machine learning model, a support vector machine, or SVM.
And they trained this SVM on nothing but the 5% fragments?
Exactly.
And what happened?
The SVM performed exceptionally well. It was highly predictive of the disease.
Wow.
And to ensure it wasn't a fluke, they ran a control test where they retained a random 5% of the data and blanked the rest.
Let me guess, it failed.
The SVM completely failed on the random data. This proved mathematically that the deep learning model had not hallucinated.
It had successfully, precisely isolated the exact 5% of brain dynamics that harbor the dysfunction defining the condition.
It reverse engineered the disease down to a 5% essence.
That is unbelievable. So let's hold up the mirror again. Biologically, what is happening in a human head to create these hyper-localized 5% dysfunctions that the AI is zeroing in on?
That's the big question.
Are we just born with a faulty circuit board, or does the brain warp over time?
Well, while genetics play a massive role, we have to look at the profound reality of neuroplasticity. The brain is not hardwired.
It's not just static hardware.
No, it is a live, dynamic, metabolically expensive organ. It is constantly tearing down and rebuilding its own physical architecture based on our environment, our experiences, and overwhelmingly our stress levels.
So the 5% dysfunction the AI spots
Often represents the physical scars of this remodeling process.
Let's dig into stress then, because the sources are incredibly explicit about how psychological stress physically damages the brain's hardware.
It's scary how physical it is. When you experience chronic stress, your body relies on the HPA axis.
The hypothalamic pituitary adrenal axis.
That's the one. This is your central stress response system, pumping out cortisol and adrenaline. It's designed for acute threats.
Like the bear on the trail.
Exactly. But when it's chronically activated by modern, unremitting stress, it becomes toxic.
Toxic meaning it alters how we feel, or toxic meaning it eats the brain?
Toxic in that it physically remodels the tissue. Prolonged stress exposure leads to a measurable reduction in the volume of the left anterior cingulate cortex.
Wait, it physically shrinks?
Tissue physically shrinks, and this is a region critical for emotional regulation and complex decision-making. Furthermore, cortisol floods the hippocampus, which is the core center for memory consolidation.
So stress literally destroys your memory.
The stress hormone impairs the hippocampus's ability to form new memories, and in severe cases, induces neuronal death.
There was a detail in the open exploration paper about this happening on a microscopic genetic level during trauma, involving things called microRNAs.
Oh, the microRNAs are fascinating.
I need you to unpack that because it sounds like stress hacks our DNA.
It doesn't change your DNA, but it alters how your DNA is expressed. MicroRNAs are tiny, non-coding RNA molecules that regulate gene expression. Under conditions of severe, traumatic, often early life stress, the brain upregulates specific microRNAs. These molecules act as repressors.
Repressing what exactly?
Repressing the brain's ability to heal itself.
Wow.
When a neuron tries to build a new, healthy synaptic connection to adapt to a situation, it sends out messenger RNA, mRNA, with the blueprints.
And the microRNAs.
These stress-induced microRNAs intercept the mRNA and bind to it, effectively blocking the translation of those blueprints.
They literally stop the brain from building resilience.
They lock the individual into a state of vulnerability and cognitive rigidity.
So when the AI maps out that 5% of salient dysfunction, it might be staring directly at the structural wreckage left behind by an overworked HPA axis and a swarm of repressor microRNAs.
Very likely, yes.
But it isn't just severe trauma that reshapes us, right? I mean, just getting through a normal Tuesday takes a toll.
Absolutely. We have to separate the concept of physical exhaustion from mental fatigue. They operate on entirely different neurological principles.
How?
When you engage in prolonged cognitive effort, staring at a spreadsheet, making difficult choices, suppressing impulses, you are exacting a specific metabolic toll on your prefrontal cortex.
Decision fatigue. This is why I can solve complex logistical problems at 10 a.m., but by 7 p.m. I can't figure out what to watch on Netflix, so I just rewatch The Office for the 10th time.
That is precisely decision fatigue. The neural circuits responsible for executive function and self-control literally deplete their metabolic resources.
Your battery is just drained.
The efficiency of the neural firing drops, and your brain defaults to the path of least resistance.
Hello, Michael Scott.
Exactly. But neuroplasticity has a flip side. While stress and fatigue degrade the architecture, intentional focused effort can upgrade it into what the literature calls elite neuroplasticity.
Elite neuroplasticity. What does the elite 5% look like? The sources use the classic example of deliberate practice in musicians.
Right. The cortex is highly competitive real estate. If you don't use a region, it shrinks. If you demand heavy performance from a region, it expands.
So they looked at violinists.
When researchers look at expert violinists, they find that the physical area of the motor cortex representing the fingers of their left hand, the hand flying up and down the fretboard, is significantly larger than in non-musicians.
The brain has literally annexed neighboring tissue to give more processing power to those fingers.
It builds a bigger engine for the task.
But the paper points out that it isn't just about adding more gray matter, right? More neurons. It's about upgrading the wiring between them.
Yes, the white matter. The researchers measure something called fractional anisotropy, or FA values.
FA values, what are they measuring?
FA values measure the structural integrity of the white matter tracks, which are the physical communication cables connecting different brain regions. In elite performers, FA values are off the charts.
Because of myelin, right?
Exactly. When a neural circuit fires repeatedly during deliberate focused practice, the brain realizes that circuit is vital. So it begins wrapping those specific axons in a fatty insulating sheath called myelin.
Like insulation on a copper wire.
This insulation prevents electrical leakage and dramatically increases the speed and synchrony of the signals. The literature suggests that the speed and flawless synchrony of these myelinated pathways predict elite performance even better than the sheer volume of gray matter.
So expertise isn't just having a bigger brain, it's having a perfectly insulated, high-speed fiber optic network.
That's a great way to put it.
Which brings us to a massive technical hurdle for our AI.
Oh yes, the memory problem.
The AI is looking for these tiny 5% flashes of altered architecture in a continuous flowing river of fMRI data. Think about how much data that is over 10 minutes.
That's massive.
How does the AI mathematically remember a tiny crucial signal it saw in minute 1 when it is constantly being flooded with new data in minute 9?
That is the defining challenge of analyzing time series data. In artificial intelligence, this problem is formally known as vanishing saliency.
Vanishing saliency. Let's unpack that. The researchers are utilizing a specific architecture called recurrent neural networks, or RNNs.
More specifically, long short-term memory networks, LSTMs.
Okay, LSTMs. Why do they suffer from amnesia?
Think of an RNN like a human trying to read an incredibly dense 1,000-page novel in one sitting.
I'm already tired.
As the network reads the sequence of brain data, step by step, it tries to hold the entire context of what it has read in its hidden state, which is essentially its working memory.
But its working memory has a limited capacity.
Right. As the sequence goes on, the mathematical signals from the very beginning of the book start to get overwritten and washed out by the new information pouring in.
Like getting to chapter 50 and realizing you have completely forgotten the motives of the character introduced on page 1, the early signal just vanishes.
Precisely. If a crucial, salient moment of schizophrenic dysfunction flashes during the first 30 seconds of a 10-minute brain scan, by minute 9, The LSTM might have mathematically forgotten the weight of that moment,
Its saliency has vanished to near zero.
which makes that post hoc introspection, the integrated gradients we talked about, completely impossible.
So the engineers had to intervene. How do you fix a neural network's amnesia?
They implemented what is known as a multi-level hierarchical attention mechanism.
Okay, we need to break that down. How does this attention mechanism change the way the AI remembers?
It abandons the idea of a single, rolling, working memory that constantly overwrites itself.
Okay, what does it do instead?
Instead, the attention mechanism looks at the hidden state of every single time step individually. It takes the memory of step 1, the memory of step 2, the memory of step 3, and it compares each one of them directly to the final overall context of the entire sequence.
Oh, it's stepping back and looking at the entire timeline laid out flat.
Yes, and to do this mathematically, it uses an operation called a softmax function to generate an alignment score for every single moment.
Wait, let's define softmax. Is that basically a mathematical filter that takes all the hundreds of memory scores and squashes them into a probability distribution so they all add up to 100%?
That's exactly it.
Meaning it physically cannot give every memory a high score. It's forced to choose what actually matters.
That is exactly what a softmax function does. It forces the network to distribute its limited attention. It creates a definitive mathematical weight for every step in time.
So it explicitly tells the network, minute 1 is vital, it gets an alignment score of 0.8, minute 2 is background noise, it gets a 0.05.
By doing this, it locks in the relevance of early moments, preserving those long-term dependencies against the wash of incoming data.
It's an elegant mathematical fix, but what blows my mind is how perfectly vanishing saliency describes modern human psychology.
Doesn't it?
We suffer from this constantly. We just call it getting distracted.
We do. And this is where the sources transition into Cal Newport's philosophy of deep work.
Ah, Cal Newport.
Newport's central thesis is that our ability to maintain long-term dependencies, to hold a complex, difficult problem in our working memory without losing the early signals, is being systematically dismantled by modern, fragmented work habits.
He introduces the concept of attention residue, which feels like the exact biological equivalent of vanishing saliency.
It really is.
Let's paint a picture. You're doing deep work, you're writing code or crafting a legal argument, holding a dozen variables in your head, and then you hear the ping.
The dreaded ping.
You switch over to Slack just for 30 seconds to answer a quick question.
A seemingly harmless context switch.
Right. But Newport argues that when you switch from task A to task B, your attention does not cleanly follow you.
And more importantly, when you switch back to task A, a residue of your attention remains stuck on the Slack message.
Your brain is still subconsciously processing the interruption.
It takes the human brain up to 20 minutes to fully clear that residue and restore its full cognitive capacity to the original task.
Which completely vaporizes the myth of multitasking.
Totally. The human brain is not a parallel processor. It is a sequential processor.
When we think we are multitasking, we are actually just rapid switching.
Bathing our neural networks in thick layers of attention residue, fragmenting our cognition, and washing out the saliency of our own deep thoughts.
So how do we fix our own vanishing saliency? Newport suggests time tracking.
Not for corporate billing, but as a diagnostic tool.
He calls it a diagnostic mirror. By ruthlessly tracking exactly when you are engaged in deep, uninterrupted focus versus shallow, reactive work, you bring your own vanishing saliency into harsh, conscious awareness.
Most people realize they rarely sustain focus for more than 15 minutes.
He treats focus like a muscle that has atrophied. You have to train your brain's biological alignment score. And to do that, he says you have to actively embrace boredom.
Which is so hard to do now.
You have to stop reflexively pulling out your smartphone the second you feel a twinge of mental fatigue in a grocery line.
He outlines philosophies for this.
Yeah, the monastic approach of total isolation, the bimodal approach of retreating for a few days a week, or the journalistic approach of violently protecting any 90-minute block you can find in your schedule.
The overarching goal is to architect an environment where your brain has the space to hold on to salient signals without them being immediately overwritten by a tide of digital noise.
But this leads to the ultimate biological question. The AI uses a softmax math function to calculate an alignment score, tagging important moments so it doesn't forget them.
Right.
Does the human brain have a physical cellular equivalent? When I'm experiencing something important at 2 p.m., does my brain physically tag it to ensure it gets saved into long-term memory later?
It absolutely does. And this is where the deep dive into the science of sleep becomes essential.
Oh, the sleep science is so cool.
The biological equivalent of the AI's attention mechanism is explained by the prime-to-sleep hypothesis and a molecular mechanism known as synaptic tagging and capture, or the STC model.
STC, the biological sticky note. Let's unpack the timeline of this, starting with when we are awake.
Let's look at the wake-sleep divide. During wakefulness, when you are engaged in learning, your brain is inducing temporary labile plastic changes in your synapses.
But it does not immediately lock those changes in permanently.
No, cementing those changes requires immense cellular energy and would cause too much interference with ongoing processing. So instead, the brain sets a temporary synaptic tag at the specific connection that was heavily stimulated.
It leaves a sticky note that says, hey, this circuit is important, save this for later.
Exactly. And simultaneously, that strong, wakeful experience triggers a process inside the nucleus of the neuron. It triggers the transcription of specific genes, known as immediate early genes, or IEGs.
IEGs, and what do they do?
These genes produce messenger RNA for what are called plasticity-related products, or PRPs.
So the nucleus of the cell acts like a factory manager, printing out the blueprints for the building materials needed to physically reinforce the synapse.
Yes, but here is the critical part. During wakefulness, those blueprints mostly just sit there.
They just sit.
The synapse is tagged, the mRNA is floating around, but the final physical construction hasn't happened. The brain is merely primed.
And then we go to sleep. We lose consciousness. What happens to the sticky notes and the blueprints in the dark?
During sleep, particularly during slow-wave deep sleep and REM sleep, the brain actively and spontaneously reactivates the specific circuits that were tagged during the day.
It essentially plays back the salient experiences.
And this specific reactivation during the chemical state of sleep is what triggers the translation of those blueprints.
Translation in biology means turning the mRNA code into actual physical proteins.
Correct. The sleep state triggers the synthesis of the plasticity-related products right at the location of the synaptic tags.
Wow.
These proteins physically alter the architecture of the synapse. They add new receptors, they expand the dendritic spine, they physically permanently stabilize the structural plasticity.
So wakefulness writes the sticky note, but sleep is the filing clerk that actually puts the document into permanent structural storage.
If you don't sleep, the tags fade, the mRNA degrades, and the memory or the skill simply vanishes.
That is the harsh biological reality of vanishing saliency. Our brain's attention mechanism relies entirely on sleep to calculate and finalize the alignment scores of our daily existence.
It really is a perfect parallel.
Which perfectly sets the stage for our final revelation. We've seen how the AI learns the baseline, how it isolates the 5% of dysfunction, and how it uses an attention mechanism to remember what's important across time.
Now for the results.
Right, let's look at the actual results. What did this model discover when it applied all of this math to the 3 massive medical data sets?
The researchers unleashed the pre-trained whole millicy model on OASIS for Alzheimer's disease, FBRN for schizophrenia, and ABIDE for autism spectrum disorder.
And what was the first major observation?
Well, it was how the pre-training baseline interacted with the different data sets.
Right. The paper notes that the pre-training gave a massive performance boost for accurately classifying Alzheimer's and schizophrenia, but it didn't help nearly as much with the autism data set.
Yeah.
Why the discrepancy?
It comes down to demographic age matching.
Age matching.
The pre-training data, the Human Connectome Project, is comprised almost entirely of healthy adults. The Alzheimer's dataset and the schizophrenia dataset also primarily consist of adult brains.
Therefore, the baseline dynamics the model learned translated beautifully.
Exactly. But the autism dataset, ABIDE, contains a massive proportion of children and adolescents.
And a child's baseline brain is a completely different landscape than an adult's.
Radically different due to explosive ongoing neurodevelopment, pruning, and myelination. The model's adult baseline didn't map perfectly onto the younger dataset.
It's a stark reminder of how dynamic and constantly shifting the brain is across a lifespan.
Absolutely. But the truly groundbreaking part of this final stage wasn't just where the model found the dysfunction in the brain, the spatial mapping.
It was when it found it, the temporal dynamics.
Yes. The researchers moved beyond simple functional network connectivity. They wanted to measure the temporal densities of the disorders.
Temporal densities.
They wanted to know, does the 5% of discriminative brain activity happen in short, violent bursts? Or is it a flat, continuous hum spread evenly across time.
And to measure this mathematically, they used a metric called the Earth Mover's Distance, or EMD.
Earth mover's distance, yes.
The simplest way to visualize this is a pile of dirt in a field. If all the dirt is gathered into one incredibly tall, sharp spike in the exact center of the field, moving out, that dirt requires a massive amount of concentrated effort.
That is a high EMD.
But if that exact same amount of dirt is spread out perfectly flat, a millimeter thick, across the entire field, shifting it around requires very little effort. That is a low EMD.
Exactly. The researchers used this math to see if the brain's dysfunction was a spike of dirt or a flat line.
And the results were profoundly revealing. For schizophrenia, the temporal density was highly focal. It had a high EMD.
It was spiky in time.
The discriminative events, the mathematical markers that define the disorder, happened in distinct, sudden bursts of abnormal activity.
Spatially, when these spikes occurred, they showed a widespread predictive pattern, primarily involving the cerebellum interacting erratically across multiple cortical domains, driving sensorimotor changes.
Alzheimer's disease showed a very similar temporal profile, right? High EMD.
Yes. Alzheimer's was also highly focal and spiky in time. The brain would be humming along, and then a sudden, dense burst of discriminative dysfunction would occur.
Spatially, for Alzheimer's, these predictive features heavily engage the visual and cognitive networks, disrupting their normal flow.
But when the AI looked at autism spectrum disorder, the math told a completely different story.
In stark contrast, ASD showed a uniform temporal density. The EMD was remarkably low.
The discriminative features did not happen in sudden bursts or misfires. The altered activity was a constant underlying state, spread evenly and flatly across the entire timeline of the scan.
It wasn't a sudden event interrupting the brain, it was the baseline hum of the brain itself.
Exactly. And spatially, ASD showed the least between domain connectivity. Instead of erratic crosstalk, the model highlighted intensive within-domain changes.
It showed hyperconnectivity within specific cerebellum, sensorimotor, and subcortical domains, but significantly less broad communication between those isolated domains. I want to spend some time here bringing this back to the lived human experience. We have this complex AI math, Earth mover's distance, high spikes, uniform flats. But what does it actually mean for a human being that Alzheimer's and schizophrenia are spiky temporal disruptions, while autism is a uniform temporal state?
This takes us directly into the philosophy and neurochemistry of consciousness, referencing Elaine Perry's work.
Oh, Mary, yeah.
It reminds us that consciousness isn't just a software program running on static silicon hardware. The brain is a chemical bath.
Our conscious reality is dictated moment by moment by shifting tides of neurotransmitters.
So how does a spiky temporal disruption feel to the person experiencing it? Think about the theater of the mind.
Right.
In schizophrenia or Alzheimer's, based on this AI's analysis, the disorders represent dynamic, sudden misfires. They are spikes of chemical or electrical disruption that momentarily hijack or distort specific networks.
For an Alzheimer's patient, this aligns with the lived experience of having periods of relative lucidity, only to have the spotlight of attention suddenly flicker, fail, or get lost in a fog of sudden cognitive disruption.
The theater is functioning, but the power supply to the spotlight surges and drops unpredictably.
And for schizophrenia, those spikes might manifest as sudden, intrusive sensory broadcasts, hallucinations, or delusions that violently seize the spotlight for a burst of time before subsiding.
Exactly. But autism is mathematically different. It's uniform.
Autism presents as a universally different baseline wiring of consciousness itself. It is a continuous, uniform state of processing the world.
The spotlight of attention isn't flickering or misfiring. The theater itself is fundamentally constructed with a different architecture.
The AI's finding of intense within-domain connectivity mirrors the intense, focused, specialized processing we often see in ASD, while the lack of between-domain connectivity might explain the overwhelming nature of trying to integrate massive amounts of chaotic social and sensory data all at once.
It is not a broken operating system. It is a continuously different operating system.
That is an incredibly profound and empathetic insight to pull from the cold, deep math of a neural network.
It bridges the gap. It proves that deep math, when applied correctly, maps directly onto deep biology and human empathy.
Let's pull this entire journey together. We started with the raw, chaotic, high-dimensional static of a resting human brain inside an fMRI tube.
We watched an AI framework, the whole EEL-LC model, learn the fundamental baseline rhythms of a healthy spotlight of attention.
We saw it use an attention mechanism and a softmax function to conquer its own vanishing saliency, remembering the vital clues across time.
We validated its findings through the ruthless RAR method, proving it could isolate the exact 5% of brain dynamics responsible for severe dysfunctions.
And at every step, we saw how the AI's struggle mathematically mirrors our own biological reality. We saw how our brains use acetylcholine and dopamine to focus the theater spotlight.
How chronic stress and runaway microRNAs physically damage our neural architecture.
How we battle our own vanishing attention residue through deep work.
And how sleep serves as the ultimate biological alignment score, translating temporary synaptic tags into permanent structural changes.
It is a phenomenal mapping of the mind. But I want to leave you, the listener, with a final provocative thought.
Always good to end on a high note.
Throughout this entire deep dive, we've talked about how these researchers successfully use this AI framework to reverse engineer the 5% of brain dynamics that define disorders.
They mathematically isolated the temporal and spatial blueprints of schizophrenia and Alzheimer's.
They meticulously mapped the architecture of human dysfunction. But imagine the flip side of that coin.
What do you mean?
What if we took this exact same highly validated AI framework and instead of feeding it the fMRI data of a patient struggling with a disorder, we fed it the scan of a master violinist mid-performance?
Oh, wow.
Or a chess grandmaster seeing the matrix of the board? Or a writer executing 4 uninterrupted hours of flawless deep work in a profound state of flow?
That completely flips the paradigm.
Yeah. If an AI can precisely mathematically map the 5% of neural activity that constitutes a breakdown of consciousness, it means we are only steps away from using that exact same math to biologically reverse engineer the absolute peak of human potential.
We can mathematically isolate the exact rhythm, the precise temporal density of genius.
We could map the perfect optimal spotlight.
That is incredible to think about.
Exactly. So the next time you sit down to focus on a difficult task, the next time you choose to guard your attention against the noise of the digital world, ask yourself, if we put you in the scanner right now, what does your 5% look like?
Are you letting it vanish into residue, or are you actively building it?
Because the ultimate diagnostic mirror for the mind is finally starting to work, and the picture it's painting is entirely up to you.